Hello, we are going to continue on discussion for chapter 5. So today we are going to talk about the monochromatic illumination and how to get the image from a lens. So what we are going to consider is the following coordinate. Okay, so we have a object is here, and then object has a coordinate x eta, and then we call u0 as object field scalar component. And then there is a distance between the object and the lens, and it has a z1. And on the lens, we have a coordinate x and y. And we are going to assume that the lens is thin enough. This ui and ui prime is ul and ul prime is nearly the same. And then we are going to talk about the, the free space propagation to z2, and then we get the image at the image plane, and the coordinate is going to be ub, and we are going to have a ui as an image field. So we are going to correlate object field with the image field by a certain function, which is we called impulse response or point spread function of this imaging system. So this concept is very important. This is a very simple case. We have an object and the lens and the image here, but it could be a very complicated lens and aperture system. But anyhow, whatever that is, we are going to correlate the object field with the image field via the impulse response or point spread function of that imaging system. Okay, so depending upon the structures of an imaging system, it will have a different impulse response. It will have a different point spread function. That is, and we need to find out this h. And then mathematically, ui is actually given by u0 convolution h. This is our simple mathematical form. So once you know the impulse response, then image field can be found by simply convolution. Okay, this is what we are going to do. The most familiar properties of lenses is their ability to form images. Okay, which are the distribution of light intensity that closely resembles the object. Okay. The image can be real in the sense that the actual distribution of intensity appears across the plane behind the lens. That means, as in this case, image is going to form behind the lens, not before the lens. If it is formed before, we call the virtual image. It is after the lens, we call it a real image. So we are going to concern only the real image case. So here we consider image formation in only a limited context. We restrict attention to the positive, aberration-free, thin lens that forms a real image. Okay, we consider only a monochromatic illumination. So we are not going to think about there is multiple colors. There's a single color. Okay, so that's our rather stricted assumptions. So this is our system. Please remind that object has a coordinate θ, lens has a coordinate xy, and the image has a uv. Okay. So what we want to do is that we want to have this relationship. Image field at the image coordinate ui ub is correlated by object field at the object plane with the impulse response, HC, in terms of a convolution. Okay. Okay. So the properties of an imaging system will be completely described by the impulse response, okay, H. So we need to find out in our cases what is the H in this our system. To produce high quality images, UI image must be as similar as possible to U0 object. So equivalently, the impulse response should closely approximate as a Dirac delta function such that HUB xi eta would be similar to this one, such that the U and xi coordinate is correlated by scale factor of m or magnification factor m. Then any point in the xi is correlated by the u in this way. So that means u is plus minus m xi, and the v is also plus minus m eta. So whatever xi eta is formed, and then it's going to be projected into u v. Okay, it's a linear, and then it's just the scale factor. Okay, so that is the geometrical case. If we have a certain lens and it is determining the magnification factor, depending on the positions, right? We know that in the geometrical optics, the magnification factor is going to be determined by location of the object and location of the image and the focal point of this one. Okay, so there's a magnification factor is going to be coming out, but we are dealing with the wave, and we are dealing with the diffractions. So the main concern here is that we have this lens which has a certain phase variation, but also it has a aperture. Okay, it has a kind of aperture. So we call pupil function P, along with the phase change. So basically, it's a kind of diffraction problem. We have a aperture here, circular aperture, and then within the circular aperture, we have a certain phase change. And then we want to find out what is the diffraction pattern at Z2. Okay, so that's the way to change the argument from the geometrical optics to the wave optics to include the impact of the diffraction. Okay. So to find out the impulse response, let the object be the delta function so that it is a kind of point source. So point source at the coordinate xi eta. Then the incident on the lens will appear as a spherical wave, so that we have at the xi eta, just a point source, and then it's going to come in light, and then we will have a lens. And then in the paraxial approximation, we have already discussed that the spherical wave can be approximated in this quadratic phase in paraxial approximation. This is the spherical wave. Spherical wave in paraxial approximation. And then this will correlate the xy, the lens coordinate, and then this is the correlate the cosiata of our object. Okay, so after passing through the lens of the focal length, then we have a ui prime is given by ul. I'm sorry, I'm just keep on making mistakes. ul prime is given by ul times full field function with this phase changes within the lens. Okay. So what we have considered is that we are going to assume that there's a point source, and then we calculate the ul, and after passing through the lens, we have to consider the full field function and the phase changes, and then we can get the ul prime. And then after that, it is going to be diffracted. And then we can use the scalar diffraction theory to correlate ul prime and the ui. Okay, so we start with the point spread, point light source, and then it reached to the just before the lens. We calculate the ul, and then right after the lens, you calculate the ul prime, and then from here you get the free space propagations. Okay. So the first case is that we get the spherical wave arriving at the lens, and after passing through the lens, we get this relationship. P is the full field function, and this is the phase change of the lens. And then finally, using the Fresnel diffraction equations, the ul prime is going to be ul prime times the quadratic phase. Quadratic phase is going to be our h functions. Okay. So basically, this is the u0, uo, right? Actually. But we start with the point spread functions, point source, so that we get the h here. Okay. So if it is not a point source, then we get u0. But for the point source, point light source, we get h. And if we have a u0, uo, then you get ui here. Okay. So we have to consider all the phase factors. Remember, this is the famous scalar diffractions quadratic phase, right? And then if you change it, and then eventually what we could get is here. So it is correlating the cosiata, the coordinate in the object, and the coordinate in the image. And in the way of doing this, we have to consider xy, which is the lens. Okay, so we have a lens full field functions and the lens phase. Okay, and then we get this phase terms here. So if you look at it, we have a 3 quadratic phase here. and here, and here. Okay, and we have to do something about this, and then we can further reduce this rather complicated relationship into a more simplified one. Okay, so first thing is that uh, two quadratic base terms, u square, v square, cos square, eta square, here, is independent of the length. Is independent of the length, and only one term. This is the depend on the length coordinate. And to make the calculation simpler, and then we choose this vector is going to be 0. And then this is nothing but classical lensmaker's law. So we get the image when Z1 and Z2 has a relationship like this. And then we have images like this. So by choosing the lens law, lensmaker's law, is actually to get the optimal point spread function or impulse response. Okay, so if we have this one surviving, it's going to be very messy. So lensmaker's law will simplify the calculations, and that means it will have a clear image. Okay. So this term will vanish if we choose this one. Okay, this is the lensmaker's law. And then quadratic phase factor that depends only on the coordinate UB. That means the object space. This term can be ignored under either two conditions. Just read this one. So that means it could be neglected. And then for the quadratic phase, for depending on cos eta, it can be also neglected in those three conditions. So if we neglect all three quadratic phase terms, then we end up with this. So we have a Fourier function with this Fourier transform like effect here. Okay, and but of course, if you look at it, you'll find out that there is a kind of a relationship: cos z1, u z2, eta z1, v z2. Remember that. From here to here is a z1 for the object. C eta, and then we have a z2 u v. Okay, certain relationship will have this coordinate summations here. And then once again, P is the Fourier function of the lens. Okay. And then we are getting close to our conclusion of today. So we get the impulse response. Impulse response. Of lens. So if you look at it, the lens characteristic is included in the P. Okay. And this factor is actually going to be a kind of a Fraunhofer diffraction. Or if you look at it, it's just a Fourier transform, and that means we are considering the Fraunhofer diffraction of the lens. And then we are going to further simplify the term. So we are going to have a magnification is z2 over z1, but in this case, you should know that 1 over f. Okay. Under these assumptions, we define the magnifications m equal to z2 over z1, and then we get the relationship between the z2, z1, z1, z2, z2 is going to be changed into a magnification factor, and then we get this relationship. Okay. Thus, if the lens law is satisfied, impulse response is seen to give up to an extra scaling factor of 1 over lambda z1 by the Fraunhofer diffraction pattern of the lens aperture centered on image coordinate u minus m psi, u equal to m psi, v equal to m eta. So everything is projected onto image plane by the multiplication factor according to geometrical optics, but we should add the impact of diffraction by lens. Okay, we have a lens, that means we have an aperture, and then we get the diffraction. So of course, in the case of this one, it is Airy functions, right? So if the image system is perfect, then the image is simply an inverted and scaled replication of the image like this. Okay. And then under this case, we have to have the point spread function is going to be delta function. Okay, delta function. And only this delta function will give you this type of form by convolution. Okay. To include the effects of diffraction, we return to the expression 5.33 here. So we have to, this is the ideal or geometrical optics. And then we have to change the coordinate once again, and then we get this relationship. Okay, and you get the HUB xi eta is actually HU minus xi, and xi eta v minus. Okay, because only this function is given here. And then if you look at it, if you change the coordinate once again, then you get the point normalized point spread function with the normalized object, and then this is given by convolution. Okay, convolution. And then here, geometrical image is actually this one. So here, what we can say is that H, normalized H is nothing but, here, this is the point spread function introduced by the diffraction of the lens. Pupil function, and this is the Fraunhofer diffraction. So in fact, it is the Fourier transform, but you can say that it is the Fourier Fraunhofer diffraction. So to tell the story, long story short, we get the image by a convolution. And our geometrical image is a magnification replica of object with the scaling factor, which is in fact determined by the magnification number, and then this point spread function for the lens system is nothing but here is given by Fraunhofer diffraction of the lens. Two main conclusions obtained is that the ideal image produced by the diffraction limited optical system is scaled and the inverted version of the object, and the effect of diffraction is to convolution, that the ideal image with the Fraunhofer diffraction pattern of the lens profile. Okay, so this is the main conclusion. So geometrical image convoluted with the Fraunhofer diffraction by the profile function. Okay, so if the lens is circular, that's just a circular aperture. So what we are going to next is that we are going to increase the number of lens and the apertures, and then we will see some kind of a new technique, and then that is called operator notations. And then we are going to talk about some of the operators, quadratic phase exponential, that is nothing but the propagation in the free space, and the scaling by constant is a kind of a magnifications, and like this, okay. And then by using these operators, we can have a series of optical system, and then we can do fairly easy calculations, not by tracing how the light field is going to change at every different optical element. So that's the topic that we are going to talk about in the next class. So once again, our conclusion here is this. So geometrical image is convoluted with the point spread function of the lens system, which is the Fraunhofer diffraction pattern of our profile function. And then we get the images. Okay, I will talk about it at the next class for different cases. And then we'll see more complex optical system. Thank you.